Okay, a very good afternoon to everyone. Thank you for coming to our tutorial for the last chapters of this module on mainly on the, it's not exactly risk assessment, but we are here to show you different tools to use to calculate like what is the reliability rate, what is unreliability rate, and also mean time before failure for one system. This is important for us to do, especially if any of you are planning to work in maintenance department or process engineering, where you will have to actually plan for when to down your machines for maintenance, preventive maintenance. So the MTBF, mean time between failures data, are very important for us to know, okay, if I have this set of system, how often do I need to down them for just to change valve or to do some cleaning up, etc. Okay, therefore we focus more on the reliability, the unreliability, and the calculations. And also later on, I'm going to go through what is event tree and also fault tree. Okay, so let's take a look at these first questions. The water flow to a chemical reactor cooling coil is controlled by the system shown in figure 1, where let me just make it bigger that you can see. So in this system, we have a pump, and then we have a flow transmitter, controller, and level control valve. By the way, this is the wrong system, yeah. The one that being shown here is just to show you like how we calculate it. But in reality, we will avoid designing a pump and followed by a control valve, because every time when we throttle the control valve, we actually throttle the pump. Yeah, so most of the time the pumps will come in, it go through certain process, and the valve will come before or after. Okay, most of the time after, unless that control the valve is an on-off valve to let the flow go or let not the flow go. Okay, if not, if you put constantly put a control valve like this, like what is being shown in the system, we are actually constantly throttling the pumps. Yeah. So this is just for your information, but for practices purposes, we are allowed to look at the system and to do a calculations like what is the reliability rate, what is the unreliability rate, what is the overall failure rate, and also the MTBF for the system. Okay, assumes this is a 1 year periods of operation. Okay, so you have been shown, this is the data done by, oops, sorry. This is the data that is done by the safety officers or maintenance departments, that they have tested again and again on all these controller, control valve, flow meter, for be it fluids or even solids or partials or dual flow, and also etc., and pressure measurements and all that. Okay, and they also estimated what is the fault per year, means the failure per year of each of these individual instruments. What you are seeing here are instruments, yeah. So they are not, they are part of the process, but they are instrumentations of the process, mainly on control system. So you have come across all this in another module called process control and instrumentation. So the whole list here are all the process components. These are the instruments, yeah. So the fault per year here is what we say as mu, okay. So from this table, we have, from this control system, we have a flow transmitter, we have a controller, and we have a control valve. Okay, so from this table, the failure rate, okay, means the mu here for, let's see, flow transmitter, means our flow measurements in fluid is 1.14 per year. Okay, our the controller, the flow controller, is 0.29 fault per year. Okay, you can see it from this data here. So the controller 0.29 and the flow measurements 1.14, which is our flow transmitter. The control valve 0.6. Okay, so we have one more, and the mu valve is 0.6. Okay. So if you have read or watched my video, you know that the reliability of each of the item is what we call reliability rates per time is e to the power of negative mu per time. Our t here is 1 year. Okay. So in that case, you can just put in this value RT for the flow meter. So e to the power of negative 1.14. So anyone has the answer? If not, I need to pull out my calculator. Exponentials to negative 1.14. Okay, I got it. 0.31. Thank you. 3198. Okay, same thing. Do it for the controller. E negative 0.29. And also the reliability for valves. E negative 0.6. Okay, so this one is 0.7483. And for what? Okay, thank you. 0.5488. Okay. So the overall reliability, okay, overall process reliability. Okay, so when we look at this process, okay, this is a series, meaning it comes here, it comes here, it comes here. Okay, and what the series means is that every time when one fail, all other fail. So if we have this one fail, this whole system is fail. If we have a controller fail, the whole system is fail. Or when we have a valve fail, the whole system is fail. Okay, so meaning the reliability becomes very, very small. So when we look at overall process reliability, the reliability in total is always go with phi, okay, and I equals to 1 Ri. So what does this phi mean? It means R1 times R2 times R3 all the way until Rn. Okay, so why do we times it? What does the data, how does that significantly tell us? Because you can see reliability plus unreliability means reliability means that how reliable, how often, the statistics of how often your process work. And unreliability means how what is the probability of your process fail. Okay, so when we have a total reliability plus unreliability, the percentage is 100%, because when the time that the process is not failing means the process is working. Okay, does it make sense? So the total statistics in here is reliability plus unreliability equals to 1. So the data is always in fractions. So in another words, is percentage of how reliable or unreliable your system is. So when we have a series system like this, okay, the one that you look at, and one fail, everything fail, we take the total process reliability, we times all the reliability values of each individual components. So in this case, we have 0.3198 times 0.7483 times 0.5488. Okay, so what do we get? I get something like 0.1313, so which is 13.13% of reliability. Means if I were to say how unreliable this system is, it means it's like unreliability 1 minus 0.1313, I have about 86.9% of time that these equipments will fail. Okay, meaning 86.9% of the time that these systems fail. Is that bad? Okay, so meaning if I were to really plan for a preventive maintenance, I may have to do a preventive maintenance quite often for this system in order to make sure it is running, because the reliability time means the uptime for this machine or this process is only 13%. Okay, because one of these fail, the whole system fail. But if we have a system, okay, that is like one fail, it does not affect others. Like for example, if you have parallel WAF, you have two WAF. So if WAF A doesn't work, WAF B will kick in. So to have both WAF fail at the same time, the unreliability is very small. In that case, the calculations for overall process reliability will be the numbers of unreliable times each one of them. Okay, so that's where then you will know that what is the unreliability and reliability of the system, because that reduces the chances of failure for the system. Okay, so we have reliability here 13.3%, 86.9% unreliable. So it answers the questions. The overall failure rate is okay, we haven't come to that yet because we have to translate back into view into the mu. We have the unreliability, the reliability, and the mean time before failure. We are going to calculate these two, the overall failure rate. Okay, so now we have the overall unreliability value. So again, just now we already mentioned the reliability rate is RT equals to exponentials to power of negative mu t. So exponentials to negative mu t. So we have this RT as 0.1313. Okay, so and we know this is 1 year period, so we have ln 0.1313. Okay, so let's see what's the data. So this is 2.03 times failure per year. So remember, the mu is always talking about how often or how many times it failed per year. You can see here, fault per year. So if we are to translate, we can say this is how many times it fails, or 2.03 fault per year. In another words, how often does it break down? Is one. Often does the system breaks down? Is 1 over mu. So in this case will be 0.4925 years. So if we are to times 12, so it's like almost every 5.9 months, it breaks down. Does it make sense now? So if we are to plan for a maintenance, so this one, when we say how often does the system break down, it has another name called mean time between failure. So this is our MTBE, which is 5.9 months. So if you are to plan a preventive maintenance for the system, and you say, oh, I will do a preventive maintenance every 6 months, can it work? Anyone? The answer is no, because before 6 months, the systems were already, one of these, whatever you're looking here, would have already break down. Okay, be it the flow meter, be it the controller, all the valves will have already break down, because the breaking down expected time is 5.9 months. So if we are to plan every 6 months, it's too late, because before the preventive maintenance, the system will already fail. Okay, so if we are to plan for a preventive maintenance for this system, I would suggest you to do before, shorter than this periods. Means it really depends on how your company works. Some companies say, oh, we can do it like every 5 months, doesn't matter. But some companies say, oh, I want a breakdowns in terms of year. So in this case, we can do maybe 3 times per year. So every 4 months, I would do a preventive maintenance. And then it comes to, when it comes to end of the year, I will have completed enough amount of time for me to run the preventive maintenance. Because if you're planning it every 5 months, means you will have an overlapping. It's like this year, maybe you do May, October, but then next year it will go to March. And then you will have to add another 5 months to August, and the calculations become very messy. So a lot of company, they prefer to cut their maintenance, the preventive maintenance is under the periods of 1 year, how many times? So we know that this system, if 1 year, 2 times every 6 months, not enough. So we break down to 3 times. So 1 year, every 4 months, we do it once. Okay, so preventive maintenance is under scheduled downtime. Yes, this is the planned scheduled downtime. Hold on, I think I have another meeting that I forgot to reject. Just give me a minute to reject the meeting. Sorry, let's get back to here. Any questions so far? So we have roughly covered a few terms that has been used in maintenance engineering. The overall failure rate, the unreliability, the reliability, and the mean times before failure, MTBF, sorry, not E. It's failure, so it's F. Okay. Any questions? So I saw that there's one question, is preventive maintenance is under scheduled downtime? Yes, it is. Okay. And any questions so far? If not, then we proceed to the next questions. Next tutorial question, because this one I don't spend too much time into all these calculations, because most of the time we won't be using these calculations unless you are in process engineering, where your job is to plan for preventive maintenance. And if not, most of the time, if you buy equipments, your supplier will be telling you, will be the one who advise you, okay, how often that you need to do a preventive, we call it PM, because they are the one who knows that how many components are there in their system. Because sometimes when we buy a machine, it's like a black box. There's so many things inside. And it's up to the supplier to tell us, oh, these machines, you need to do preventive maintenance every 3 months, every 6 months, or twice a year, or once a year. So it really depends. And how do they define that? Is all depending on the component that they use. And because these data are being studied, and these are some old data, this is 1986. So some of this data may not be practical for the latest switch or controller anymore. So if they have done their own company study, that they know, oh, I'm using a more Chang'e, a more high-tech controller, that's the fault per year is actually 0.5 or even 0.7 per year. They may be able to give you that data, because that will be their in-house testing data. So what we are seeing here, the table 12.1, is the generic data that if let's say we are looking at general form, and you don't have the data from, because every company, they have their in-house testing data, and they might not be able to give you, to them that might be their own company properties or confidential data. And they will only tell you, okay, our equipments, the reliability, or they won't call that reliability, they will say you need to do maintenance twice a year. You know that, okay, so meaning what all the components inside, the calculations is based on what we have. Oh dear, is based on what we have here. Okay. So the calculations will not change even for the next 20, 30 years. It will still be the same. But this value, the one that you're looking at here, okay, sorry. The one that we are looking at here, they might change. Okay. These are the one that they might change. So it really depending on, oh, did I accidentally move it? I think I did. Okay. Any questions so far? If not, then we can take a look at the next questions. So question 2, this is very important, yeah. So pay attention to this question so that you don't miss out anything. Okay, water storage system, tank system in this figure is a standard storage system for chemical and water. Okay, and we also know that overfilling of the storage tank is really common in process industry. And to prevent overflowing, the storage tank is equipped with a high-level shutdown system. And the high-level shutdown system is connected to one valve that will stop the flow of the input stock. So this system, let me zoom in and take a look at it. Okay, so we have a level transmitter, means we have a level flow level sensor. Okay, and then we give us a level signal that go to a level controller. And then from this level controller, it will decide, okay, now the input is too much. We need to close the valve to 50% or to close it down to 30% or whatsoever. It will then go to the level control valve to off it. Okay, So we also have a second system that is not being drawn in here, but it's being written down here, that is equipped with a high-level shutdown system, okay? So this high-level system is an external system, okay? This will shut down this. Oh, okay. Yeah, it will shut down this. Okay, so we have a level controller here, and there is a solenoid valve, which is this one, I believe. This one. Is this. Okay, so when it started to go to very high level, it would just shut down the whole thing. So this is the high level switch system. But the system seems to have also a high level alarm. Okay, so high level alarm, also from here, level signal, when it goes very high, okay, it has an alarm system here. It will ring. So in the events, if let's say the switch system doesn't kick in, the alarm ringing. So what we can do is the operator may come in and just off the valve manually. So we have an automated system in here, a control system, an automated shutdown system, and also an alarm to call for the operators to shut down the system when the level is too high. Okay, so we want to know that how often do we have a potential overflow case? Okay, if given that we have a failure here, the level indicator fail 5 times a year, meaning the indicator most likely I will assume is this level transmitter here, they fail 5 times and they can't give you a correct answer to say, oh, there is a high level, so now this whole thing just go off. Okay, so how often that we have overflow for this system? Okay, so in order for us to do the what we call the event tree, okay, so event tree come with this level 1. Level A, the event A is the indicator failure. Okay. And we have a high level alarm. So the system has, so when this fail, the water go high up. I think something is missing from my system because it cannot be from the same system, because if it's from the same system, then these things fail, everything else fail. Let me read the questions carefully. I'm so sorry. I cannot move it. Okay, hold on here. Okay. The storage is equipped with high-level shutdown system. Okay. The high-level shutdown system is connected to a solenoid valve that closes this system. So let me reread the whole thing again. Okay. So to prevent overflowing, it is being equipped with this system, which we can see it is this one. Okay, so this is the high-level system. It's connected to this valve. Okay, develop an the system failure of level transmitter as initiate. Okay, so yep, we are going to do this. So overflowing. So apparently this is just the control system. It seems to say that the storage tank is equipped with high level shutdown system, connects to valve to stop the flow of input. So it seems like there is another one that will come here, not just the control, because this is a control system. Okay. So that's this system will shut down here. And also we can know that there is a high level alarm here. So beside this, there is also an alarm. Okay, but we still have the system that will fit that will fail. Okay, so first thing, if let's say indicator fail, okay, we have the first level, the high level alarm system. Okay, so when high level alarm system rang, what happens is we have the third level, that operator shutdown system. And when operator fail to shut down system, okay, we have this high level switch system. But if all these fail, then we want to see outcome. Okay. So we have this indicator that rang. Okay. So this is where our level transmitter fail. So 5 times a year. Okay, and it says that the failure demands for the alarm is 0.01. So we assume the top is it passed and the bottom as a failure. So 0.01 as the failure for high level alarm. So 99% of the time it will ring. Okay, so assuming when it doesn't ring, okay, but we still have this. Because if it doesn't ring, operators are not notified. We assume that the operator won't shut down the system. Okay, so when the operators shut down the system, when it rang, operator shut down the system, how often that the operator can stop the flow is 0.2. Okay, the failure, so means 0.2 times 20% of the time the operator doesn't manage to stop the flow. But 80% of the time, the operators can stop flow. Okay, so once it stops flow, so this is safe, meaning it's already stopped. The event stopped there. But this one continue because it doesn't allow the operator to stop the flow. So it comes to here. And high-level switch systems will say that 99% of the time, it will shut down the system. 0.0% of the time it fails. Same thing with here, the operator doesn't shut it down. So 99% of the time it managed to switch and shut down the system, and 0.01% of the time it does not. So this one's safe because it shut down the system, but this is where we call the runaway, the overflow, the overfilling. Does it make sense to look at this system in this way? Okay. So we want to know how often, okay, because the question asks us, estimates the number of overflow expected per year, okay? So now we can see that let's use this color, it's overfilling here, okay? So we follow this path. Okay, so there are two paths here. Path A, that overfill here. So this is path A, path B. So let's look at path A. So the failure 5 times a year, okay, times 99% of the time it works, but 0.2% of the time it does not, because the operator doesn't shut down, okay, and also 0.01% that the high level switch system doesn't kick in. Okay, so what is the level here? So this is 0.0099 failure per year. This is on path A. So path B, okay, again, still 5 times per year, okay, and 0.01 over here, okay, and 0.01. So 0.0005 failure per year. Okay, so the total failure is where you add these two up. Okay, so path 1 plus path 2. So A plus B. So equals 0.0104 failure per year. With all this system in place, meaning how often will it fail? Is 0.0104 failure per year. So if we are to look at how long would that take to fail, all you need to do, or failure, how often it failed. It failed, or we call the mean time between failure, is 1 over mu, which is this one, 1 over 0.0104 . So 96.15 years. So if we are to look at these valves, okay, sorry, this level transmitter, even though it failed 5 times per year, with the systems that we have in here, okay, it is saying that the overfill or overflow will only expected to occur once every 96 years. So do we want to take actions about this? I think it's pretty safe, means almost like once every 100 years. So as long as we maintain our valves and all that, the systems, because we have 3 check gates here. We have the control system as it is. We have one high level shutdown system that is independent from the system. And then it comes with an alarm, because it's written here, there is a high level alarm here. So with this, the failure is once every 98 years or 96 years. So what happened if we remove one of this? If we want to compare, like, do we really need so many systems, like so many we call it the safeguard in the system? Because sometimes company may say, you see, we don't, it has been like in the last 20 years, we never use this system. Can we remove them? If some of you has looked at the Bhopal case in India, okay, there was 64 systems that has been shut down. Okay, all this system is what we call a redundant system, but for safety purposes. Like what you're seeing here, this alarm, okay, this high level indicator that shut down the same valve here, okay, this system will not kick in until we have an overflow. And when this system kick in, it only happens like 1 in 96 years. Okay. So for company that has run 20 years, this that engineer put in this system, sometimes company will say, hey, do I still want to maintain this alarm? Do I still want to maintain this high-level shutdown system? Because maintaining it every year, I have to pay 20K just to change the alarm, just to update the shutdown system. Sometimes the company may have decided not to do that. So let's take a look if what will happen, because that as an engineer, it is our job to say, can we do that or can we not do that? But if we say yes, we do not have the data to back us up. And if we say no, we need data to tell them, no, you cannot do that. So this is where we can actually redo this, what we call the event tree. If let's say the company decided, okay, the high level switch system is too expensive, I'll keep the WAF. And I'll keep the alarm. So when the alarm rang, my operators will shut it down. So now all you have is only this system. We no longer have D here. Okay, this is an example to show you how we can defend our case to see, can we remove it or better not to remove it? Okay, so what happens if we remove the high level shut system, meaning it will only comes here. Okay, so let's redo this. It's easier to redo it and then. Okay, so now we still have the level A, the indicators. Okay, the fault, failure. And then we have alarm, level B, we have alarm. Okay, and level C, we have operator shutdown. The system, okay, because D is no longer there. So now alarm rang 99% of the time. Like what is being said here, failure is 0.01. The failure here is, sorry, this is 5 times a year. Okay, and so alarm didn't ring. Will the operator shut it down? The operators most likely won't see. So this is a runaway system. Okay. So, and the operators only manage to shut down 80% of the time, and 20% of the time it fails. So this one's failed again, and this one managed to close it. So let's take a look at, we have here path C and path D. Okay, we can do both at the same time. So total failure, system failure. Is 5 times per year, okay, times 0.99 times 0.2 plus again 5 times per year times 0.01. You can see what's the differences now. This is 1.04 per year. And if we are to make it mean time between failure, is my calculations correct? So 0.99 times 2.02, yes, 1.04. So 1 over 1.04, now we notice that we have an issue here. Because this will tell us every 0.96 years times 12. So, which is, sorry. which is 11.5 months. Do you see the difference now? When we have one system in there, just with that high-level auto shutdown system, the potential runaway or overfilling of this water tank occurs once every 96 years. Okay? Removing that, we are expecting the system to break down to overfill or overflow every 11.5 months, meaning from 96 years to almost once a year. So it is okay if this is water, you just waste some water, but it is not okay if this is a chemical storage tank. You have this overflow. If this is a flammable chemical tanks, means you have flammable chemicals that is overflowing to the surrounding, and that it evaporates and fire may just occur. So now with this data, can we justify it to our bosses to say, sir, this is a very bad idea to remove this system? Or is this a good idea to remove it? And they will ask you why. You can just show them this data. Look, we have this system in place that will prevent overflowing, and it will actually causes the statistical calculations that how often it fails. The mean time between failures is 96 years. Yes, this system has been there for the last 20 years, and we don't see it in play because we don't have, because according to statistics, it will not happen in 20 years. It only happens once every 96 years. But if we remove this, by end of next year, you will see us having this overflowing or flooding the plants with some chemicals. So this is how we can justify why the system is needed. Why do we put in redundant safety measures in our process plant? Okay, Ken, any questions, class? So this is the true purpose of running an inventory. Okay, so when we want to do this, like even if, let's say, you want to justify, for example, you don't have the system and you have a storage tank that always overflow, and you did these calculations and you say, okay, prof, boss, we want to put in this auto shutdown system, and the boss says that shutdown system costs me 100,000 ringgit. It's so expensive. Why do I want to put that in? Then you can show him, okay, right now, if we don't put it in, so we have overflow every 12 months, we need to clear the space up. But the moment we put it in, we don't have to worry about it for the next 95 years. How about that? Okay, so these tools help you to justify both end. Okay, can understand? Class? So make sure you know how to draw an inventory. Yeah? It's very simple. You just have to read, okay, follow the system here. The systems tell you step by step. Is step one, high level alarm. You just, okay, so high level alarm here. Then let me change color. Okay, operator stop flow, the second one. So you just follow exactly the sequence. Okay, this is going to be very, okay. Yep, so you just follow the sequence and put in the numbers that you can calculate the probability. So this chapter focuses a lot of probability in accidents, in preventing accidents from happening or incidents from happening. Any questions, class? Ken? So this is the purpose of an inventory. Okay, so you start with an event. The event is not fire, is not something, but it's some things that we know it has a failure. Like it can be a valve failure, indicator failure, that will lead to a runaway system. So your runaway here is overflow. Some of your runaway system may end up in fire and explosion. Okay, so that depends on until what level we stop. Any questions so far, class, before I go to the next questions? Yes, the next question is using the same questions. Yeah, but we look at the fault tree analysis. Okay, can? Okay, good. So let's take a look at part B. So this is question A that asks us to do an event tree. So question B, same questions, but we start with a different event. So event tree always start with some instrumentations failure that leads to the incidents that we want to avoid. Fault tree always starts with the top events that is something that we want to avoid. That's something that we want to study. For example, overflow, or for example, fire and explosion. Okay. So the top events here, we were asked to start with storage tank overflow. Okay. So normally it's circle. Okay. And then if we are to look at the system, we follow the system, we look at the system itself. Okay, so it overflows. It can be because of level transmitter failure. Because remember just now we say this is a when we have one fail, we have everything fail. So if this fail, the whole system fail. If level controller fail, the whole system fail. If controller fail, the whole system fail too. If the alarm fail, the whole system fail too. And if the high level indicator fail, the whole system fail too. Okay, so means but if this system fail, but this system kick in, so this is an OR here. Okay, we know that this is N. One fail, anything fail. Oh, sorry. Any of this fail or any of this fail, this will fail. But you need both to fail the system if we have this system here. Okay, so this become an AND gate. So you want, if let's say I say this is system 1, this is system 2. Okay, the system 1 is our normal control system. When the system 1 fail, but we have system 2 in place, it will help us to prevent the overflow. But if we have system 1 and system 2 fail at the same time, then it would definitely be an overflow. Okay. So in this case, we have the events here, the top events is overflow. So we have what is this called? An AND gate here. Okay, so both systems must fail. So you have system 1 and system 2. Okay, so in system 1, now we have an OR gate here. Okay, because any of this fail, it fail. Right? So system 1 here, we have an OR gate. So what do we have in system 1? We have level transmitter, level signal, level controller, and controller. So we have system 1, we have a transmitter, level controller, and a WAF. Okay, so system 2, we have also an OR gate here. Okay, or we need an AND gate because the OR gates will seems to be. So what could cause system 2 fail? Because we know that system 2, we have an alarm. Okay, and also we have a high level shutdown system. Okay, can. So alarm here, it depends on operator, shutdown, system. And this one, no, this is just one side. Okay, so this is only one line. Okay, so let's take a look at each of these failure rate. So of course, we can break it down to smaller failure. What could go wrong with the level transmitter? Maybe it's old age, maybe it's die on arrival, maybe we use a faulty valve, or it's manufacturing faulty, etc. Same with controller, same with one. You can go down into each one of them. But for us, we stop at what we can control, because if it's failed, we change them. But why is that failed any further is under manufacturing, unless you are in the, for example, you are working in a valve manufacturing, then you want to break down, okay, this valve failed here, I have 5 parts that can fail, and each parts, what are they, what are the potentials that it fails, and what could go wrong. Okay, but if we are not, as a user, we most likely will stop at here to look at the faulty rate. Okay, so here we have this level transmitter. Then we will have to go back to the first table that we have. Okay, where is my original table? Okay, here we can use back this table. So we again, it seems that we are looking at the same thing again. We are looking at controller. So let me just clean up here a little bit so that I have a bigger picture to look at. Okay, just now we have one flow measurements, again fluid, control valve, and also controller. Okay, on the system 1. So we have 0.29, 0.6, 1.14. So help me to remember. So controller 0.6. Okay, so this is controller mu is 0.6. Transmitter is, which is the level measurements, 1.14, and the other one is 0.29. 1.14, this is 0.29. And this alarm here we have is the failure rate is 0.01. Okay, the failure rate of our operator is 0.2, and this one is 0.01. Okay, so if we are to calculate what is the statistics of how often that the system breakdown, if we are to use according to this, remember this is an AND gate. Okay, so let's look at the OR gate here first. So this is OR also. Okay, we will look at system by system. Okay, so system 1. Okay, so we have mu for transmitter 1.14, mu for controller 0.60, mu for valves 0.29. So again, we want to translate this because it's an OR gate, means anything fail here, the whole system won't fail. So we want to look at the reliability of, remember just now when we talk about reliability is exponential minus mu t. Okay, since this value is the same, okay, and it's all OR gate, so the answer will be exactly the same as the first questions where you did these questions. So we have our total reliability here, because we already did that just now, 0.3198, 0.7483, 0.5488. So the overall process reliability, okay, so maybe I'll just copy down the answer here. So let me just remember the numbers. So flow, okay. So R for level transmitter, okay, which is 0.3198. Remember just now Naga has given me the flow controller, the R for controller is 0.7483, and R for valves is 0.5488. So overall reliability R total is again I equals 1 and Ri. So means you have RLT times RC times RV. So again, same thing with thanks Naga for putting the value in here, 1313. Okay, so the overall reliability for this is 0.1313. So we want to know the mu here. Okay, mu total for this system is 2.03 fault per year for system 1. Let me put a different color. Okay, so for system 1. Okay, so if we are to look at here, so this mu here is 2.03. So let's take a look at system 2. Okay, system 2, we need to settle this first. So this is very straightforward, the failure. Okay, mu1 and mu2, and when number 1 fail and comes to number 2, okay, so this is, hold on, this go back to when the alarm fail. Okay, so it will be 0.01. Okay, when operator fail, because this is one line, so it will be 0.99 times 0.2, because the alarms will have rank, and so meanings that the opportunity for the operator to fail is 20%. So over here is, go back to a bit of calculations in the event tree just now. 0.99 times 0.2, we get 0.198. So these two add up the total plus 0.01. So we get 0.208. So the mu here is actually 0.208. Okay, this is how we calculate, because this is a direct line down. So when alarm fail, it will fail automatically. But when alarm rang, the operators fail to restart the system is 20%. So it goes with this one. So the total unreliability of this alarm system is 0.208. Okay. So then we have this shutdown as 0.01. So again, this is all gauge. So we are going to convert this into the calculations that we did just now. Okay, for system 2. Oh dear, I don't have enough pages here. Sorry, forgive me for that noisy sound. Where's my? Okay, now I have a new page. Good. Okay, so now we look at system 2. Okay, let me put back in black. Okay, so system 2, we have alarm system. Okay, so this one, overall alarm system, we have 0.208, and also the high level shutdown system is 0.01, the failure. Okay, so reliability of this is negative 0.208, and this is negative, oops, sorry, 0.01. So this is 0.8122. And again, this is 99%. Okay, because we know that your reliability is 99%. Okay, so now, again, this system is an OR system, so you need both to fail the whole system. Okay, so it goes back to overall reliability. Is phi Ri and I equals to 1. So 0.8122 times 0.99. So equals to 0.8041. Okay. So if we are to look at what is mu, it will be negative mu equals to ln 0.8041. Okay, am I doing it correctly? So this will be 0.218. Okay, for the system 2. Okay, so now system 2 here, our mu is 0.218. We need both systems to fail for us to have an overflow here, and this is an AND gate. Okay, so when we have an AND gate, the calculations is different from when we have an OR gate, because OR gate means we look at the reliability. When any of this failed, the whole system failed, but we need both to fail at the same time in order for the storage tanks to overflow. So we know that in this case, if we are to put these two, okay, the calculations, oh dear, I don't have enough space again. The calculations will be the overall unreliability for both systems. Okay, to do the calculation. So in this case, we'll have the P for this one, system 1, will be 1 minus 0.1313. So this is 0.8687. So the unreliability here, P for system 2 is 1 minus 0.8041, which we have 0.1959. Okay, so overall unreliability in this case is PT is 5, okay, 1 I equals 1N equals to on P, okay, meaning P1 times P2 here. So we have P1 0.8687 times 0.1959 0.1702. Okay, so again, if we are to calculate back the reliability, so R here, total is 1 minus 0.1702. So we have it back 0.8298. And so mu equals to negative ln 0.8298. Is 0.1865. Okay, so mean time fault per year. So the overall system in this case, the overflow overall is 0.1865. Okay, mean time between failure is 1 over 0.1865. Is 5.3 years. Okay, so if we are to use event tree and fault tree to calculate, we will notice that the numbers are very different because depending on our calculation. Any questions here? Here they shows that if we have the system, two systems together, the mean time between failure is 5.3 years. If we are to use fault tree. Okay, if we are to use event tree to calculate, then the failure is 96 years. Any questions so far, class? So this is how we use event tree and fault tree. There's no saying which one is better, okay, because both are different tools. Okay, so a lot of company, they will prefer to use event tree. Some company, they prefer to use fault tree. Because fault tree, sometimes you can put in more data in here. Okay, because this one we talk about AND gate here, we talk about the system here, and some company, they even go to multiple systems and to see what can they do to prevent it from happening, or even they want to go very deep down into each of the component. Okay, so it really depends on company, which one do they want to use. What I'm doing here is to show you that both can be used, but be aware that both actually give you different answer depending on your calculation. Because over here we say this system will fail when system 1 fail and system 2 fail at the same time. But it doesn't take into considerations that system 2 is actually a safeguard for system 1. Yeah, so that is the lacking of the fault tree in this scenario. Whereas when we use this event tree to do this whole calculations, what happened is that we assume that the system 1 is already failed, okay, 5 times a year. That's the assumptions. That is where we didn't even calculate, we do not calculate anything in this system at all. This system, you notice that we didn't calculate anything. We straight away use that, okay, when these systems fail, we have a secondary system to cover it up. And that calculation based on the secondary system. But the calculations for fault tree is very different. It's saying that when we have system 1 and system 2 at the same time, System 1 fail, we still have system 2 to cover. And when system 1 and 2 fail, then the whole system fail. It doesn't use system 2 to be a safeguard for system 1. You see the differences in here? Class? Yep. So that's how we use both are not wrong, by the way. Both are correct in how you present your data. Okay, in this case, we are saying that this system, you need both of them to fail in order to have the system failure. And in this system, we are saying that system 1 fail, doesn't matter, we have a backup system. So system 2 is mainly for backup purposes. Any questions, class?